The final topic I want to address in this particular section of security engineering is how do you know that a trusted system is trustworthy? You don't want to individually go through an extensive process of evaluating the security for yourself on each case in an independent basis. So this brings us to the topic of security evaluation, certification, and accreditation. Now, the first point I want to make here is that Orange Book is the Trusted Computer Security Evaluation or Computer System Evaluation Criteria, TCSEC. Interesting point about this is that I know from an insider source that this is no longer examinable, but it's still in the common body of knowledge, which suggests there are things in the CBK, that other things that may not be examinable, but you still have to know about for some reason. Now, I don't know exactly what those are, I just know this is one of them. Now, TCSEC started back in the 70s, 80s. It has 4 different divisions, as they're called. Division A is the highest, verified protection. Division B is mandatory protection. That's where we typically have multi-level security. It's mandatory access control systems. Division C is discretionary protection, where we're using, obviously, discretionary access control. And Division D is minimal security. We'll talk about that in the next slide. Now, bear in mind, this was the first of these kinds of evaluation and certification frameworks and standards. So it was developed back in the days when everything was funded by US government. They were only concerned about confidentiality. They weren't so much concerned about integrity. Also, it's designed to apply to only multi-user mainframes and mini-computers, standalone boxes, not networked systems. These were systems that had terminals plugged in rather than having more sophisticated networking. Now, they did attempt subsequently to produce a thing called Red Book, which one of the various different rainbow series of books, which you can find at www.kernel.org. So Red Book is actually trusted network implementation. It tries to sort of map to the TCSEC divisions, but it's not as formally well defined because TCSEC is based upon all the mathematics that underlies things like Bell LaPadula, etc., whereas there wasn't any equivalent kind of consideration given to network security. But yeah, the various rainbow books are produced by the NSA's National Computer Security Center, and they cover a range of topics. For example, the Teal book deals with password hygiene. They're of historical interest only these days. And I guess that TCSEC, or Orange Book, falls into that kind of category as well. The problem is that people still use the terminology like mandatory protection or C2 versus B1, etc., etc. So it's helpful to know about it. Now, as I mentioned, Division D is minimal protection. I call it the epic fail division. It has only one class in it, and it consists of everything that tried to meet evaluation at a higher division, but failed. Right? So nobody ever brags about having achieved TCSEC certification at Division D. It doesn't mean much at all. But C1 and C2, remember this is discretionary access control. C1, discretionary security protection, says you must have access control based on users and groups. You must supply a protected execution domain so that privileged processes are not affected by lower privileged processes, and that's either rings or the supervisor mode versus user mode. There must be some specific ways of assuring system integrity, like, for example, hashes or digests on the system critical files. There has to be some documentation, some design documentation, a test plan, various results, a facility manual for installing and configuring the system, maybe, and certainly user manuals. But strict access control and auditing is not required. C2, controlled access protection, does require more granular access control plus auditing. And it must also allow for object reuse protection, so that you shouldn't be able to actually read disk space that was freed up by someone else deleting a file, for example, and freed memory or allocated memory must be zeroed out when it's allocated to you. You might recall in days of Windows NT 3.51, Microsoft bragged about achieving C2 certification for Windows NT. Well, yes, they did. But remember, it only applies to standalone systems. So we're talking here about a Windows NT machine with no network connection, but also no USB ports, no floppy disk drive, no kind of CD burner, no ability to actually remove information from it. You could just simply sit at it and work, and that was suitable to achieve C2 level certification. So it's nothing really to write home about at that level. Things start to get really interesting when we come to Division B, mandatory protection. Now, while we go backwards through the alphabet, the security levels actually go up through the numbers. So the lowest level here is labeled security, which is B1, which is the basic Bell LaPadula system. Okay, classifications and clearances. It applies to Bell LaPadula rules. Data leaving the system must also be labeled, and the security policy is based on an informal statement. The design specifications do get reviewed and verified. Upper level is B2, which is structured protection. You now have to have a clearly defined security policy. System design must be more thoroughly reviewed and tested. Processors must be in distinct address spaces, but the segmented architecture of the Intel processors assures that. The system must not allow the storage covert channel between different security levels, and it must provide a trusted path for logons, e.g. the secure attention key. You're obviously aware that on PCs, Control-Alt-Delete gives you the guaranteed logon a dialog or a pop-up that says, what do you want to do? Change your password, switch to a different user, log off, lock the desktop, etc. It's not always Control-Alt-Delete. Other hardware uses different techniques. For example, Trusted AIX on IBM P or Power Series processors, P systems, uses Control-K, if I remember correctly, as the secure attention key. B3 is security domains, the highest level here. It's a simplified design. Again, further simplify it. Complexity is the enemy of security. You get more granularity in each protection mechanism. It mustn't allow the timing covert channel. It must be able to recover from failure securely. It must always boot securely. And it has a distinct security administrator role as from the system administrator role. The security administrator role, he's responsible for example, relabeling resources, maybe responsible for provisioning user accounts, resolving various issues with access, etc. It's distinct from the system administrator who does things like backups, etc., etc. Finally, at the top level in TCSEC, we have A1, which is verified design. Now here we're using formal methods to actually prove the system to be secure and correctly designed. So you get all the same kind of features and functionality as B3. The security policy model maps very formally to the TCB. It has very stringent change and configuration management. Now the very first system certified to A1 was a thing called SCOMP, Secure Communications Processor, which is used to actually route orders from the Pentagon going out through the US chain of command. It was a derivative of Multics running on a modified Honeywell Level 6 minicomputer. Now, interestingly, while it was certified to A1, when the time came to recertify it, Honeywell simply told the DoD, hell no, we've been through this once before. It was horrendously expensive. If you want this, you will buy it. And in fact, that's how they dealt with its successor, XTS 300. Now, it was only evaluated to B3. But, at the Pentagon, for example, the first Gulf War, etc., the Pentagon generals would work out the order of battle for the following day or whatever. And then that needs to be actually disseminated down the chain of command to the individual fleets, air wings, etc., etc. And then you've actually got to, within an air wing, for example, break it out to the individual squadrons, then to the individual pilots. Now, while the generals have got a TSSCI clearance, etc., some of these pilots maybe only have a secret clearance. So you've got to actually selectively declassify the orders right down to the individual level. Of course, as you break it up, and the level goes down to the individual squadron, for example, because it's not as sensitive at that level, you can declassify it from top secret to secret or whatever. Right? And that's what XTS 300 was supposed to do. It was the time-phased force deployment data system, which would route the orders by breaking down the order of battle for the following day, and then routing components of that to the individual fleets, air wings, etc., and then within each air wing out to the individual squadrons, etc., declassifying it automatically. So it was a trusted subject or a trusted principle. This is a fairly common theme, that doing this to this level is extremely expensive. I've seen estimates that at the time this was at its peak, there were only about 200 people worldwide who were capable of doing the A1 verified design type stuff, both design and evaluation. So similarly, the Blacker crypto processor was A1 certified, but then later on, Motorola, with its network encryption system, said, no, screw this, we're going to just do it to B2. If you want it, you will buy it. And that turned out to be true. Now, one problem with TCSEC was that it focused entirely on functionality. You know, the system had to have certain functions like access control, logging and auditing, authentication, intrusion detection, etc., etc. That would say how sophisticated or complicated it was. Remember, complexity is the enemy of. And what was more important, the Americans were ignoring, was how well designed is it in terms of actually complying with a security model, etc. And that's a matter of assurance, which is different from functionality. So the Europeans were on top of this with their standard called ITSEC. And they would evaluate the assurance of the security components in terms of the documentation, looking at the development methodology, configuration management, testing practices, as well. You get assurance by both reviewing the design documentation, but also doing tests on it. Different systems could have the same functionality, but very different assurance levels. And in fact, the more functionality you add, the harder it becomes to assure the security components. Now, all of this eventually got so expensive and complex that it was not really feasible for individual governments or even the EU to do it by themselves. So eventually, they all got together and came up with the Common Criteria Project, which was largely driven by Europeans, but also a lot of American input. They had gone through an intermediate thing called the Federal Criteria, but then that was adapted into ITSEC, or with ITSEC, to come up with the Common Criteria Project. Now it performs the certifications against what are called protection profiles. I've lost my copies of protection profiles I'll refer to the next slide. I've got a paper copy of one of them floating around, a couple of them floating around somewhere, but I don't have the original PDFs and I haven't been able to re-download them subsequently. But essentially, a protection profile is quite a long written document. We'll see the structure of it in a minute, which is intended to be implementation independent. So you should be able to evaluate lots of comparable operating systems against a particular protection profile. But actually, they've been developed not just for operating systems, for other things as well. So protection profiles are reusable, they aim to be useful, effective, etc. And you can download the current set of protection profiles from the Common Criteria portal given on the slide. Now, protection profiles have been developed for a whole range of things like firewalls, relational databases, smart cards, etc. There was an attempt at one point to come up with protection profiles for mobile phones or smartphones, but the technology there was moving far too fast. They found it very hard to hit the moving target there. For operating systems, I've downloaded, but I've lost 3 different protection profiles. There's one called the Controlled Access Protection Profile, which is written by the NSA and is very like TCSEC C2 level classification. There's also one called the labeled security protection profile, which is like TCSEC B1, B2. It's more like B2 really. Those actually are good examples of how the protection profiles are structured. There's also one written by somebody else, which is not as formally well written, called the RBAC, Role-Based Access Control Protection Profile. Now, protection profiles always have the same format. There's a descriptive element that gives you the background information. There's a rationale, which is what this protection profile is intended to achieve, and systems that are evaluated against it are intended to achieve. Then you've got the functional requirements, the things it must do, which is a bit like Orange Book. But you've also got the development assurance requirements, which is all the documentation to be analysed, etc. And you've got the evaluation assurance requirements. How are we going to test this thing? Now, at the end of an evaluation, you'll end up with an evaluation assurance level. The lower levels are actually fairly easy to achieve. I mean, EAL1, functionally tested, effectively says, we kicked the tires, it didn't fall over. That's about all we can say about it. EAL2, structurally tested, does require some design information and test results from the developer. 3 means it was methodically tested and checked. So that's actually going after the evaluation assurance. But also EAL4 looks at the development assurance. Was it methodically designed? Was it tested? Was the design reviewed, etc.? Now, EAL4 is probably about as high as you can get with commercial off-the-shelf software, operating systems, databases, whatever. I know that, for example, Red Hat Enterprise Linux has been evaluated at EAL4 for both the controlled access protection profile and the labeled security protection profile. And in fact, it was actually evaluated at EAL4 Plus, or EAL4 Augmented, which means it actually got some of the things in EAL5 as well. Bear in mind that this was, again, for a hardware-software combination. It's the operating system on a particular platform. So this was all done by IBM, I believe, were the ones that actually put it up for evaluation. Now, EAL5 is much, much harder to achieve. It's unlikely that you'll achieve EAL5 evaluations unless you're designing with a common criteria evaluation in mind. I mentioned earlier examples like British Aerospace, for example, designed an operating system for trusted systems that achieved EAL5. In addition, on IBM mainframes, the LPAR microcode that separates logical partitions has also been evaluated to EAL5. EAL5 is also the level at which different governments stop trusting each other's evaluations. They won't trust commercial laboratories to do the evaluations. They want to do it themselves, right? In the NSA, in ASD, BSI, whatever. So EAL6 is semi-formal, and EAL7 is a bit like A1, formally verified, designed, and tested. And as they say, it's for extremely high-risk environments. It's limited to what are called TOEs, targets of evaluation. That's the thing that's undergoing evaluation, that are amenable to extensive formal analysis. So here you're going to use formal methods to prove the security properties of the system. Now, evaluation is part of the certification and accreditation process. Certification is a technical assessment of how well a particular system complies with the various security requirements and other requirements in the protection profiles, for example. So there'll be basic evaluation techniques that are common to all potential users of the system. It'll take into account what mode of operation it will run in. Remember, trusted systems have got different modes. Who the users will be, the level of training they will have, what applications it will be running, the sensitivity of the data that's on it, the likely interconnections and system and facility configuration. Will it run in a SCIF, for example, a secure compartmented information facility, that kind of thing. So overall is a judgment of how trustworthy this particular system actually is. Okay? And you can then, having achieved certification, you can rely on, you can read the results of the certification. But then the decision to actually deploy a trusted system or to deploy a particularly evaluated product is really accreditation, because it considers the stuff that we talked about before, but also things like the actual threats and vulnerabilities, the operational concept and environment, specific interconnections to other systems, other networks, etc., the formal acceptance of the risk associated with deploying the system, and also the operational lifespan, which can be quite long. These systems are expensive to design, expensive to evaluate, to certify, and to actually accredit. And as a consequence, in these kinds of government and military environments, they're typically deployed for a very long lifespan. Okay, inside NORAD, for example, when I visited NORAD inside Cheyenne Mountain, they were running a VAX cluster, probably running trusted VMS, and even at that time, VAX and VAX computers were getting to be a bit out of date. I should imagine that they kept them running for quite some time. They may even be running them still today and buying spare parts on the open market. I mean, think about things like the B-52 bomber, which first flew in the early 1950s. And it's expected that with enhancements to the avionics and all that kind of stuff and engine upgrades and stuff like that, it'll still be flying in the 2050s. So that's a 1 century operational lifespan. That's the kind of thing we're looking at in government and military environments especially. Okay, that takes us to the end of this security architecture section of security engineering. That was a lot of material to swallow, but we're past it all. We can now move on to the next particular topic, which is cryptology.